Hi everyone, in this video we'll cover the Central Limit Theorem. There are plenty of YouTube videos out there explaining the Central Limit Theorem, but none of those I've watched gave me a full understanding of it. Most of the time I was left still wondering what it is used for. So here's my own explanation of the CLT. To begin with, let's talk about stable versus unstable random processes so as to give you a little bit of context. So there exists stable, not very complex random processes. For example, suppose that a random variable x is the number of aces drawn in 2 draws from a deck of 52 cards without replacement. We say that x follows a hypergeometric distribution with parameters n, capital N, and a, where capital N is the total number of cards in the deck, so we have 52 cards in the deck, and A is the total number of aces in the deck, which is 4. Here, N, capital N, and A do not change. They are stable. No matter how many times we repeat the experiment, we're going to find 52 cards in the deck, 4 aces, 4 kings, 4 queens, 4 jacks, etc., etc. All possible outcomes are known. We know the 52 unique cards in the deck. These are the 52 possible outcomes. We know the parameters of the distribution. And having some external factors, some hidden factors affecting the number of aces drawn in 2 draws is very, very unlikely. Another example of a stable, not very complex random process is the height of adult males. We know that the height of adult males approximates a normal distribution with parameters mu and sigma, where mu is the average height and sigma is the standard deviation. So why can we say that the height of adult males is a stable random process? First of all, we know that when we reach a certain age, when we reach adulthood, we stop growing, our height stabilizes. And we know that there are a few known factors causing minor variations in the height of adult males, most notably diet and genes, ethnicity, country of origin. These 3 factors are interrelated, so I put them together. We know that a man from Sweden is likely to be taller than a man from Japan because on average people in Sweden are taller than Japanese people. And yet you'll never see a man who's only 10 centimeters tall, nor will you see a man who's 10 meters tall. You'll never see a man with such an extreme height because the order of magnitude of the height of adult males doesn't change. From one country to another, the average height and the standard deviation are not going to change much. That's why we can say that the height of adult males is a pretty stable random process. And whether it be the height of an adult male or the number of aces drawn in 2 draws, these are 2 examples of random processes that are easy to model, primarily because they are stable and not complex. And that's the case for many other random variables: the height and weight of most animals, the number of heads obtained in 3 coin tosses, the number of 6 obtained in 3 dice rolls, and there are countless examples. These are well understood random variables whose probability distributions are easy to build. At the other end of the spectrum are unstable and complex random processes that are heavily affected by various factors. These random processes are very difficult to capture with a single distribution, with a single neat formula. And don't get me wrong, there are people who actually do try to model these complex and unstable random processes with probability distributions that partially fit them, or even with a mixture of 2 or more probability distributions. Anyways, let's take household income as an example of a complex and unstable random process. Household income is very difficult to capture with a single probability distribution because it is affected by many factors causing major variations in household income, most notably country, state, city, or even neighborhood of residence. wealth at birth, education, whether household members are employed or unemployed. By the way, these three factors are strongly correlated because when you're born into a wealthy family, you're much more likely to get a better education, to have access to private tutoring on top of regular school, and go on to study at prestigious universities with all the costs covered by your parents. And that in turn makes it far more likely that you'll end up employed with a high paying job compared to someone born into a poor family who's more likely to end up unemployed. Then you have health. If one family member gets seriously ill or disabled, that's going to take a toll on their household annual income. On top of that, you can add economic crises, inflation, and natural disasters. I mean, if you live in the US, especially in Louisiana, you certainly remember Hurricane Katrina in 2005 and the flooding and the thousands of people who lost their lives, the tens of thousands who lost their homes, their jobs, their cars, everything they own from one day to the next. Then you have wars and time itself. And all these factors that affect or may affect household income make it very difficult to find the true probability distribution of this random variable. There's too much uncertainty. Now, going back to more stable and less complex random processes, I should say that we don't always know the true parameters of the probability distribution of a given population. For example, if we take the random variable height of trees in a forest, which approximates a normal distribution with parameters mu and sigma, where mu is the average height of all the trees in that forest, and sigma is the standard deviation. Well, we don't know mu, we don't know the average height of all the trees in that forest, and we don't know the standard deviation either, because it would require measuring the height of every single tree in that forest. So we can't do that. Instead, we could take a sample of n trees, where n could be equal to 1,000. So we take a sample of 1,000 trees. We measure their heights. So we collect 1,000 heights. We compute the sample mean denoted x bar. So the sample mean is the average height of the trees in that sample, and the sample standard deviation denoted s. We could put these heights into bins of, let's say, width 5 feet, and then count the number of heights that fall in each bin. Then what we could do is visualize what the distribution of these 1,000 heights looks like. And if it looks like a bell curve, if it looks like a normal distribution, we could use the PDF and CDF of the normal distribution. Let me say it again, we could use the PDF and CDF formulas of the normal distribution along with the sample mean and the sample standard deviation to estimate probabilities, but keep in mind that x bar and s are just estimates of the true parameters mu and sigma. We've seen that we cannot find the true mean and true standard deviation of a population by taking just one sample. We can just get an estimate, an approximation of these parameters. Therefore, the probability distribution we get when using the CDF along with these estimates, so along with the sample mean and the sample standard deviation, is also an approximation of the true distribution of the population. So when you take a sample and you compute the mean and the standard deviation of this particular sample, these estimated parameters can be close to the true parameters, so close to the true mean and true standard deviation, but they could also be very far from the true mean and true standard deviation due to a high variability in the data set. So how can we find the true mean and true standard deviation of the population? In our example, the population consists of all the trees in a forest. without having to measure the height of every single tree. That's where the central limit theorem comes in. Using the CLT implies taking many samples from the population under study and working with sample means instead of the actual values. So instead of working directly with the heights of trees in the forest, we will be working with the average heights of trees in the different samples. The central limit theorem says that regardless of the shape of the distribution of the population under study, whether it be normal, right skewed, left skewed, exponential, or uniform, the CLT allows us to find the true mean and the true standard deviation of this population by taking from the population lots of samples of size greater than or equal to 30. For example, let's say that our population is once again all the trees in a forest. We could take a first sample of 30 trees, a second sample of 30 trees, a third, and another one, and another one. The idea is to get as many samples as possible. Then we're going to compute the average height of the trees in each sample. So this formula says that we are going to compute the average height of the trees in sample 1. This is a summation symbol in math, and it says that we need to add up the heights of the trees in that sample from the very first tree to the 30th tree, because n equals 30. And the sample mean is denoted x bar. Then we repeat the process for sample 2, for sample 3, for sample 4, 5, etc., etc. Here I stopped at 3 samples, but you get the idea. We take as many samples as possible, and therefore we're going to calculate as many means as there are samples. And once we've done that, we can finally compute the mean of the sample means. We take all the means we've computed earlier, we add them up, and we divide by the number of sample means we have. So here in my example, I've got 3 samples, so 3 sample means. I'm going to divide this sum by 3, and that's going to give me the mean of the sample means. So let's recap real quick what we've done so far in our example. We've taken a bunch of samples. We've taken many samples. We've calculated the mean of each sample. In other words, the sample mean. We now have as many sample means as there are samples. Then we've calculated the mean of the sample means, and the CLT says that the mean of the sample means is equal to the mean of the population. It's equal to mu, a parameter that was unknown, because remember, we cannot measure the height of every single tree in a forest, so we couldn't find the average height of all the trees in that forest. But now we know, thanks to the CLT, we know this parameter. And the CLT says that the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. We know n, it's the sample size. In our example, it's equal to 30. And the standard deviation of the sample means can be calculated because we have the sample means and we've computed the mean of the sample means. So we can calculate the standard deviation of the sample means also. And once we've done that, we can find the standard deviation of the population. In other words, the CLT allows us to find both the mean of the population and the standard deviation of the population. Let's keep going. The CLT states that if the probability distribution of the population is normal, and in our example, the probability distribution of the population is the probability distribution of the height of trees in a forest, remember? Then the probability distribution of the sample means will also be normal regardless of sample size. And more importantly, it states that the probability distribution of the sample means will approximate a normal distribution whenever the sample size is at least 30. And that is true for any population regardless of the shape of its underlying distribution. If you visualize the sample means on a histogram, then their probability distribution should look like a bell curve, should look like a normal distribution if the sample size is at least 30. So let's connect the dots now. Why is the CLT so useful, and how does it contribute to the popularity of the normal distribution in data science? Well, we've seen that the CLT is all about working with sample means instead of the raw data itself. The CLT states that provided that the sample size is at least 30, these sample means will approximate a normal distribution. And it turns out that some widely used statistical tests consist of comparing means, sample means, and they are performed using the probability distribution of the sample means, which is assumed to be normal. If the assumption of normality is violated, the conclusions drawn from these statistical tests may be unreliable / misleading. But thanks to the CLT, as long as the sample size is at least 30, we can use the properties of the normal distribution to perform statistical tests on sample means instead of the raw data itself, even if the samples themselves were taken from a population whose probability distribution is not normal. In other words, if the probability distribution of the population is not normal and the sample size is less than 30, then the probability distribution of the sample means will not approximate a normal distribution, and consequently we won't be able to use the properties of the normal distribution to perform these statistical tests. And finally, let me provide you with some important clarifications. The sample size of 30 or more is just a rule of thumb, not a law. Sometimes you'll see people using sample sizes less than 30, but usually the greater the sample size, the better. For the mean of the sample means to be exactly equal to the mean of the population, every single individual in the population needs to be sampled. If I go back to my example, for the mean of the sample means to be exactly equal to the average height of all the trees in the forest, every single tree in that forest needs to be sampled. So we need to take many, many samples so that every single tree ends up in at least one of these samples. But usually we don't do that. In practice, we don't do that. And for the distribution of the sample means to look normal on a histogram, so the distribution of the sample means is also called the sampling distribution of the sample means. We need the number of samples to be large enough. Otherwise, the distribution of the sample means is going to look noisy. That's the end of the video. If it was helpful, then please share, like, comment, and subscribe. If you want to support my channel, which is far from being monetized, I'm light years from being monetized, you can buy me a coffee. Just follow the link on the description below. Again, thanks for your attention and see you in the next one.